Viewers, today we are going to see about principle of moments. An ideal lever is essentially a light that is of negligible mass rod pivoted at a point along its length. This point is called the fulcrum. So this point is called the fulcrum. A seesaw on the children's playground is a typical example of a lever. Two forces F1 and F2 parallel to each other and usually perpendicular to the lever, as shown here, act on the lever at distances d1 and d2 respectively from the fulcrum, as shown in figure 723. So this is force F1, this is d1 distance from fulcrum, and you have another force acting at point B, F2, the distance is d2. The lever is a system in mechanical equilibrium. Let R be the reaction of the support at the fulcrum. So this R is the reaction of the support at the fulcrum. R is directed opposite to the forces F1 and F2. F1 and F2 is acting downwards, whereas this reactive force, reaction, is upwards, and it is opposite to the direction of F1 and F2. So for translational equilibrium, the upward forces are positive and the downward forces are negative. So R minus F1 minus F2 is equal to 0. This is equation number 1. For considering rotational equilibrium, we take the moments about the fulcrum. So this is the fulcrum. Now we are interested in taking the moments. The sum of moments must be 0. That is d1 F1 minus d2 F2 is equal to 0. So if you take, we have two notations. One is anti-clockwise, is positive, and clockwise is negative. So if you see this is clockwise, whereas this is anti-clockwise. So normally the anti-clockwise moments are taken to be positive. So anti-clockwise means this is positive. That's why we are putting d1 F1 as positive, whereas clockwise is negative. Clockwise means negative. Note, R acts at the fulcrum itself. This R is acting at the fulcrum itself and has 0 moment about the fulcrum. So this will be having 0 moment. Okay. In the case of the lever force, F1 is usually some weight to be lifted. It is called the load, and its distance from the fulcrum d1 is called the load arm. So this is load arm and this is load. Force F2 is the effort applied to lift the load. Distance d2 of the effort from the fulcrum is the effort arm. So this is the effort arm, and this is the effort we are going to put at B. So equation 2, so this is equation 2, can be written as, you bring this negative term to the other side. So d1 F1 is equal to d2 F2. That is load arm is d1 into F1, that is load, is equal to effort arm, d2 is the effort arm, into effort. The above equation expresses the principle of moments for a lever. Incidentally, the ratio F1 divided by F2 is called the mechanical advantage. That is, F1, you bring this F2 this side, move this d1 to the other side. So F1 by F2, which is also equal to d2 by d1, is called the mechanical advantage. If the effort arm d2 is larger than the load arm, that is d2 is greater than d1, that means numerator is higher, therefore the mechanical advantage is greater than 1. So it will be greater than 1. Mechanical advantage greater than 1 means that a small effort can be used to lift a large load. So there are several examples of a lever around you besides the seesaw. Okay, so this is the concept of principle of moments, and we have seen what is fulcrum, what is the notation. Anti-clockwise means positive, clockwise is negative. We have discussed about load arm and the effort arm, and to have a mechanical advantage greater than 1, D2 should be greater than T1. Okay, so this is the basic idea of principle of moments. Hope you have understood this topic. Thanks for watching. Nandri.